Hi everyone, today's lecture is lecture 2.2, the second and final lecture for week 2. Today you will need homework number 3 and you'll need the homework number 3 addendum. I had forgotten to put a couple of problems attach them to homework 3, so you'll have to print this homework 3 addendum. It's only 5 problems, it's only one sheet of paper, don't panic. You'll need your calculator, your pink sheet, your periodic table, and again tonight you will need your book. Okay, today we're going to be talking about the limiting reagent concept. So in the whole topic of limiting reagents, we need to review the general form of the chemical equation. On our last lecture, we talked about the equation as starting with reactants that undergo a reaction and then producing products. Another word for reactants is reagents. So we'll be working tonight with limiting reagents, so everything on the left side of the chemical equation is of importance for us this evening. So reagents, reactants are used, that word is used interchangeably. Okay, so the concept of limiting reagents is important because one reagent is going to limit the maximum amount of product you can produce. So one reagent in your chemical reaction is going to dictate the maximum amount of product that you're able to produce. This word, you should never use a word it's something's name in its definition to describe it. So one reagent is going to limit or dictate or determine the maximum amount of product you can produce. So let's talk about a pretend chemical reaction. Let's say I want to make a grilled cheese sandwich. So in order to get my end product, I need 2 different reactants. I need 3 pieces of cheese and I need 2 pieces of bread. And if I add those things together and react them, I'll get my product, a grilled cheese sandwich. So I need 3 cheeses, 2 breads to make 1 sandwich. Okay, let's do a pretend limiting reagent problem. If I have 20 cheese slices, you know, like the Kraft ones that are wrapped. If I have 20 cheese slices and 30 pieces of bread, what is the maximum number of sandwiches I can produce? If you have 20 slices of cheese, you need 3 slices for every sandwich. So what's the most number of sandwiches you can make with 20 slices of cheese? 20 divided by 3 is a little bit less than 7. So I can make 6 total sandwiches. Now, if I have 30 pieces of cheese, 30 pieces of bread, I need 2 pieces of bread for every sandwich. What's the maximum number of sandwiches I can make with those 30 pieces of bread? 15. With 30 breads. Now, the strategy in doing these limiting reagent problems is to look at these 2 numbers that you're getting and figure out which one is the smallest. 6 is clearly smaller than 15. That means that the most sandwiches I'm going to get with these starting materials is 6. So the answer to my question is, with 20 pieces of cheese and 30 slices of bread, I can only make 6 sandwiches. Now, in my example here, what happens to the remaining reactants that aren't used up? Like those 2 extra pieces of cheese and all of those other slices of bread. What happens with that? Well, in a chemical reaction, that's called when you have reactants in excess. So in this case, bread is in excess. That means you have an overabundance of bread and it's going to go unreacted. Okay, let's do another example of this with a different pretend reaction. Now let's say I want to make a grilled cheese sandwich, but my audience likes pickles on it. So I still need 3 slices of cheese, 20 breads, and 5 pickles to make this sandwich. My sandwich has green dots on it for the pickles. Okay, so what's the maximum number of sandwiches of this variety that I can make? Now let's say I have 40 cheese slices. Let's say I have 1 loaf of bread, and I think you can get like 18 slices of bread from 1 loaf. And let's say in my 1 jar of pickles, I have, let's say it's a really big jar. Let's say I've got 60 pickles. Okay, now just look at those numbers for a minute. Can you make a guess as to which one is your limiting reagent? Well, you could kind of make a guess, but you can't really determine based on just those 3 numbers, the 40, the 18, or the 60. You have to look at those numbers in terms of how many you need for your chemical reaction. These numbers here in this pretend chemical reaction are your stoichiometric coefficients. The same principles that we are going to be using here on these sandwich chemical reactions are the same things that we'll be doing when we talk about real live actual chemical reactions. Okay, so now to figure out how many slices of or how many sandwiches we can make, we have to take 40 divided by 3 equals a little more than 13, but we have to make whole sandwiches, so we can only make 13 sandwiches. From 18 slices of bread, 18 divided by 2 is 9. And from 60 pickles, 60 divided by 5 is 12. So in this case, what's your limiting reagent? It would be the bread. LR stands for limiting reagent. So what about the cheese slices and the pickles? Well, these 2 things are in excess. And you'll just have to save those for another day when you get more bread. Okay, so let's talk about the actual process when you're using real chemical reactions. The first thing that you're always going to need to do is make sure that your reaction is balanced, or to go ahead and balance that reaction. Your second step is to calculate the amount of product produced from your first reagent. Here's where you're going to use that stoichiometry path that we talked about in lecture 2.1. And then you're going to do the same step, the same thing that you did in step 2 for any other reagent that you're given information about. Now, in step 4, we're going to compare the amounts of product. The reagent that has the smaller yield, in other words, the reagent that gives you the smallest amount in terms of product is going to be your limiting reagent. Okay, just a few tips for you. The first tip is a major mistake that a lot of students make. we do not add the amounts of products that we get from steps 2 and 3 on the previous slide together. Because you are only, just like we didn't add together when we were talking about the bread and the cheese, we didn't take the 6 and the 15 and add them together to come up with some ridiculous number like 21. You can't make 21 sandwiches from these ingredients. So just like we did not add here, we cannot add in the real chemical equations. So do not add the amounts of products together. That's a real temptation for students. Another tip that I like to have is to circle the limiting reagent in the original chemical reaction. This helps you to clarify your work. A lot of times, finding the limiting reagent might not be the only thing that you're doing to solve a problem. So to keep your workspace clear, it's helpful sometimes to circle which one is the limiting reagent. That'll help you solve later parts of the problem. Okay, let's do an example of a real chemical equation here with these concepts. Okay, so here's my chemical equation. Step 1, balance. Is it balanced? Yes. Okay, so then, moving on, let's read the question. If 5.2 grams of carbon and 2.16 grams of oxygen are reacted in the lab, where 2.04 grams of copper is, oh shucks. Aha. Okay, I'm sorry. That was an example for later on. Let us find an example. Aha. Let's take this example. CH3OH is methanol plus carbon dioxide yields acetic acid. Okay, so firstly, just check to see if it's balanced. It is balanced, that's convenient. Okay. 5.1 grams of the methane is reacted with 3.25 grams of the carbon monoxide. How much product can be produced? Okay, step 1 was to balance our equation, we did that. Step 2 is to use our first reagent and calculate how much product we can produce. Okay, so our first reagent here is the methane. So let's just set up a whole stoichiometry problem here for the methane. What goes in the second bracket? What goes on the bottom? Grams methane. Here it is. Your formula weight is 32.04 grams. And that's always per 1 mole. Here's your tricky step. All of the coefficients in this equation are 1. What is species B? It's your product. Acetic acid. Now, whenever a question asks for amount, it almost invariably means that it wants amount in terms of grams. So we're going to need to calculate the molecular weight of acetic acid. and that is 60.03 and per 1 mole. Okay, so if you do this math, divided by 32.04, you'll get an answer of 9.556 grams of acetic acid, CH3COOH. How many sig figs should you have? Only 2. Okay, so step 1 we balanced. Step 2 we calculated using the first reagent. Let's do that same thing for our, the second reagent. Okay, carbon monoxide is 28.00 grams. Okay, here's your tricky step. What is your species B? It's still that product, the acetic acid. This molecular weight is the same as you calculated on the last screen. Okay, so this answer then is going to be times 60.03 divided by 28. The answer is 7.043 grams of CH3COOH. How many sig figs should I have? 3. Okay, now let's compare this to what we had before. We had the 9 from the methane. We were able to come up with 9.6 grams of the acetic acid. Who's your limiting reagent? It's whatever reagent produces the smaller amount. So here, the 7.04 is going to be the smaller amount of yield. Therefore, your limiting reagent equals the carbon monoxide, and this is your answer. 7.04 grams of acetic acid. Now, notice we didn't add these two numbers together at all. We're just going to be using the one that's the smaller number. Okay, I misordered my slides a little bit. I'll fix that for you when I post the notes on Joule. Okay, so let's talk a little bit about percent yield. Percent yield is the actual yield divided by the theoretical yield times 100%. Very simple formula. Let's talk about what all this stuff means. The actual yield, in other words, is the amount of product obtained in the lab. So if I were to carry out my former example, if I were to add methane gas and carbon monoxide gas to yield acetic acid, whatever amount I was actually able to measure and collect in the lab would be my actual yield. Theoretical yield then is the maximum amount produced in theory, and you calculate this via your stoichiometry problem. star there for that. This is the one that you calculate. Actual yield is the one that you get from experimentation. Okay, so why is this important? Why do we bother with this? Well, the answer is because there are things that prevent us from obtaining 100% yield in the lab. One of the major things that causes us to not have 100% yield is human error. Maybe you have unsteady hands, maybe you have a little bit of shaky hand, and you spill a little bit of your powder on the desktop. Well, it looks like a little bit of powder, but in that little bit of powder are, probably thousands of molecules that are not going to be able to react with your compound. Or you're not measuring things properly. Let's say you think that your balance is showing 2.4 grams, and really it's closer to 2.5 grams. So you're not even starting with the same calculations as what's in actuality. There's a lot of human error. There's a lot of experimental error as it relates to equipment error. So we have human error. Then we have equipment error. That would be like when you have the scale that doesn't read out properly. All of those errors contribute to the fact that you're not always going to be able to produce 100% in a reaction. Sometimes, because energy or heat or gas is evolved in the course of your reaction, you're not able to capture all of those things that are emanating from your reaction vessel. That causes you to lose product as well. There are a lot of chemical reactions that don't produce even close to 100%, even when they're synthesized in very high-tech labs where they're run by very expert chemists who are very good at what they do and are very practiced at their work. Some of those reactions only yield 30-35%. So it's important to know what your percent yield is, because that determines how much, what accommodations you need to make with starting material. Another way you can think of percent yield you can think about it as the way that we calculate percent for your grade. Let's say that your exam grade there's 100 points in your exam. That would be like the theoretical yield. Like the total possible points on an exam. Theoretically, you could get 100%. You could get 100 points. The actual yield is what you're going to actually be graded on. This would be your score. So your percent yield then is like your percent ability of reproducing, to me, evidence that you've learned the concepts that we've been talking about. So that's how you can think of percent yield in terms of things that you know about. Okay, let's do a practical example of percent yield. Okay. So we have that same chemical reaction. If 5.2 grams of carbon and 2.16 grams of oxygen are reacted in the lab, where 2.04 grams of carbon dioxide is collected, what is the percent yield in this case? Okay, there are several pieces of information here. Part of critical thinking is knowing what information is extraneous and what you should use at different points in your problem. Okay, so always take a look when you get these problems and try to identify where these amounts correlate to your chemical equation. These two things are reactants. And if you have amount information for more than one reactant, you must follow the limiting reagent procedure. Okay, so this is telling me that the first thing I need to do is calculate the limiting reagent. But I have more information. If I have amount of products as well, it means that this is what I'm going to be using somewhere in this percent yield equation. First, let's solve the limiting reagent problem first. us calculate how much product can be produced from 5.2 grams of the carbon. Always put the molecular weight here. Here's your tricky bracket. 1 mole of carbon. We're calculating for the product, so that's your second species. That's what goes up here, 1 mole of carbon dioxide. And then the molecular weight of carbon dioxide is 43.99 grams per 1 mole. You should be able to do the math. And you get a yield of, oh, I don't want to do that. 19.0 grams of carbon dioxide. Okay, now let's calculate how much you can produce with your oxygen. 1 mole of O2, and there are 31.98 grams per every mole. Here's your tricky bracket. Carbon dioxide goes on top. And then the final bracket is going to be the same as the final bracket when you calculated for your other reactant, 43.99 grams per 1 mole. And you get a result of 2.97 grams CO2. What's your limiting reagent? O2. See where I did that? That helps me for later on. Especially if you get interrupted in the course of solving these problems. Okay, now this is the maximum amount of product that can be produced with these two amounts of reagents. Okay, now let's calculate the percent yield here. The theoretical yield is the yield that you calculate through stoichiometry. Therefore, that 2.97 grams of CO2 that we calculated on the previous slide, that's our theoretical yield. That's the most we could possibly produce, all conditions being perfect. Now, where did we get that number for actual yield? This is our actual yield. How do you know that? That is, this is the amount that we are obtaining in the lab. Therefore, that's our actual yield. So that's 2.04 grams. And now notice your grams are going to cancel here. So that means you're left with just a number. And your answer should be 68.7%. So you were able to isolate 68.7% of the total possible yield that you can get from this reaction in the lab.